tutorial 6. Okay, in chapter 3, so far we finished 2 types of excitation. The first one was force excitation, and the second one was unbalance. Okay, so before I talk about the tutorial, let me talk about the transmitted force. You know, if we go back to maybe there are some questions about that. The transmitted force, it will be a section. We will talk about it, but let me explain it here. So if we have a system with spring and damper mass, and let's say subjected to a force F of t equal to F naught sine omega t. When we draw the free body diagram, we will have force here equal to kx and a force here equal to cx dot. And when you draw the forces on the ground, you will have this is kx and cx dot. So the force transmitted through the spring and the damper to the ground is the sum of the spring and the damper force. But those are vector forces. Then when you add them together, you should add them as vectors. So we go back to the force diagram. We have the spring force, the damper force, the inertia force, and this is the applied force, if not. So the force to be added, or the transmitted force to the ground is the spring force and the damper force, and the resultant is this one. This is called F of t, the transmitted force that goes through the ground. Okay, so F of t, the magnitude is square root of kx squared plus c omega x squared. And you can take x or kx common. This will be square root of 1 plus. When you take kx outside, this will be c omega over k squared. And you know that this is equal to 2 zeta omega over omega m. Okay, so I'm adding this here because there are maybe some questions about the transmitted force, and this is the way to calculate the transmitted force. This is not the total force on the ground. The total force on the ground will be plus the weight. Okay, so the ground will feel the weight and the magnitude of the force, that is the maximum. So the maximum, but usually we ask only about the additional force transmitted through because of the force. Okay, there might be some question about that. The tutorial 6 is about harmonically excited vibration and rotating imbalance vibration. There are 2 causes of vibration here, or covering the 2 types. A spring mass system in question 1, a spring mass damper system is subjected to a harmonic force. The amplitude is found to be 20 millimeter at resonance and 10 millimeter at frequency, 0.75 times the resonant frequency. Find the damping ratio of the system. Now, the type of the system is a spring mass damper system, and the force applied, the excitation is a harmonic force. Then the amplitude is equal to the derived, we derived the equation for the amplitude. It was x equal to F naught over square root of k minus m omega square all square plus C omega squared, and this is in the formula sheet as well. Okay, you can see this from the formula sheet. Okay, now the amplitude is found to be 20 millimeter at resonance, which means when omega equal to omega n. And also you can write this equation as F naught over K divided by 1 minus omega over omega n squared all squared plus 2 zeta omega over omega n squared. Okay, also this is added in the formula sheet. The question is to find the damping ratio, which is zeta, is unknown. The amplitude is found to be 20 millimeter at resonance, which means when omega equal to omega n. And also we have 10 millimeter at a frequency 0.75 times resonance frequency. So we will use the same equation here 2 times. Use this equation 2 times. There will be 2 unknowns. F naught over K is one of the unknown, and zeta is the second unknown. And you will have 2 equations, 2 unknowns. You find zeta. F naught over K, you take it as one unknown. It's ratio, and it is appearing in the 2 equations as ratio. Then it becomes as one unknown. Okay, so you will have 2 equations with 2 unknowns. The first one is a 20 times 10 to the power minus 3 equal to F naught over K over 2 zeta. This is at resonance, because when omega over omega n equal to 1, this will reduce to F naught over K over 2 zeta. And 10 times 10 to the power minus 3 at a frequency ratio 0.75. So we will use the same equation, F naught over K divided by square root of 1 minus 0.75 squared, all squared, plus 2 times zeta times 0.75 squared. 2 equations, 2 unknowns. You should be able to solve it. Okay, question number 2, shown below is the steady state response. Transient are ignored. Of a direct force excited single degree of freedom system. The mass is equal to 2 kilogram. What other system parameters you can determine? So as you can see, this is the system is a spring mass system with damper and subjected to a harmonic force F. Okay, usually we use capital F equal to F naught sine. It is shown here as cosine. Omega t. Okay, so there are 2 graphs added here. The mass is known equal to 2 kilogram. We need to find K and C. Those are the 2 parameters. So if M is given equal to 2 kilogram, we need to find K and C if the informations are given are enough. Okay, there are 2 curves. I will just use different color to show you F. This is F. Okay, shown with the blue color. So it is a cosine wave, sinusoidal, with magnitude equal to 1 Newton. So F naught is equal to 1 Newton. It is one thing we can determine, right? And the frequency or period of oscillation tau, we take from peak to peak, is tau equal to 4. And then we can calculate omega equal to 2 pi over tau. So it is 2 pi over 4 equal to 2 pi over 2 radian per second. This is the excitation frequency. And the other graph is for X. Okay, amplitude of X, which is capital X, is 3 millimeter. And it is sine wave. Okay, so X is given as 3 cosine, yes, sine, and we can measure the period and the frequency. It is the same, you know, when you take one complete cycle from here to here. This is also 4, right? From 1 to 5, it means it is 4, and it is the same frequency, so it is omega pi over 2 or times t, and X is 3 millimeter, the capital X. So it is shown as a sine wave, and the force is cosine. So this is supposed to be cosine as well, because the particular solution should have the same function of the force. So this is a 3 cosine pi over 2 t minus pi over 2. So there is phase difference equal to 90 degrees. And when is the phase equal to 90 degrees? When this is at resonance. If you check the graph of the force excitation, it's always 90 for any value of zeta at resonance. So we find that the phase is 90, it means it is at resonance. So this means resonance case. And if this is resonance case, we know that omega equal to omega n. And since omega equal to omega n equals to square root of k over m. And this is equal to pi over 2. M is known, then k equal to pi over 2 squared multiplied by the mass, which is 2 kilogram. You can find k from here. Okay, that's one thing. The other thing is that X at resonance is equal to, if not, okay, it's if not over C omega n. And this is equal to 3 times 10 to the power minus 3. If not is 1, and C is unknown, we can find C from here. Okay, so we can determine C and K from the given information. Question 3, we need to work on the equation of motion, because this is not a spring mass system. And this is the most difficult, right? That students will have problem with this, struggle to find the equation of motion, although it is very simple. Okay, for the mechanism shown, K1 equal to K2 equal to 5,000 Newton per meter, A equal to 1.5 meter, B is 2 meter, L equal to 2.5 meter, and M equal to 40 kilogram, which is the attached mass. This is a point mass. The mass of the beam is also 40 kilogram. It is pivoted at point O and assumed to be rigid. Design the dashpot, i.e. calculate C, so that the damping ratio of the system is 0.2. Zeta is 0.2. Also determine the amplitude of vibration of the steady state response if a 10 Newton force is applied to the mass as indicated in the figure at a frequency of 10 radian per second, and take JCG equal to 1 over 12 ml squared. I'm not sure about the answers, but to answer the question, there are two questions here. Find C so that zeta equal to 0.2, and find the steady state amplitude at omega equal to 10 radian per second. 10? Yes, 10. And also F naught is equal to 10 Newton. We cannot answer those two questions if we don't put the equation of motion. Okay, this is not a spring mass system that we can, which does not require derivation because already we did the derivation. Okay, so in order to answer this, we need to take an arbitrary position. This is theta. And then we draw the free body diagram. The bar is uniform, rigid, with mass m. So it means its mass is at L/2. The free body diagram, we will have a force here equal to K1 times A times theta for small theta, that theta is very much less than 1. Then this is sine theta, but we will take it as theta. And there is a spring force in this direction, K2 times, we measure from the pivot. So this will be B minus A times theta, and also a damper force equal to C times B minus A theta dot. And we have the weight, that is capital M times G, and also the, this is capital M is here, and mg, which is the mass of the weight of the bar. Okay, the weight of the bar is located at L/2. So this distance is going to be L/2. And then we take sum of moment about O equal to J theta double dot. Okay, and it will be summation because we have two masses. Okay, so sum of forces, sum of moments equal to the sum of J theta double dot. Okay, regarding the left hand side, we have K, we start from the top. K1A theta times the perpendicular distance, which is A cosine theta, and A cosine theta is A. So it's going to be minus K1 A square theta. And the forces, other forces will be minus K2 times B minus A times B minus A again, so it becomes squared, times theta, minus C times B minus A times B minus A again to get the moment, times theta dot. Okay, and we have a plus because mg is doing clockwise moment in the same direction of theta. It is mg times L/2 minus A, and the moment is clockwise. Yeah, we need to get the force is vertical. Okay, then it is the distance will be we need sine theta. So this will be L/2 minus A times theta, because sine theta is theta. So we take theta very much smaller than 1. Sine theta is theta, and cosine theta is 1. And plus, this is minus mg. Mg is also doing a counterclockwise moment, minus mg times L minus A
دكتورة
times theta. Yeah.
ام جي مع البار مو المفروض زيرو؟
moment يكون زيرو
لأنه بيكون داش بالبار يعني حول البيفت.
لا يعتمد على وين السنتر اوف جرافيتي اوف ذا بار. إذا كان at O then it is zero, but if this is not necessarily at O. Okay, and you can check this by L over 2 minus A. Okay, so I assume that L over 2 minus A is less than A. It might be not true, but this will be corrected by the sign here. Okay, so I'm assuming it is above the pivot. Okay, L is equal to 2.5 over 2 minus A, which is 1.5. So this will be 1.25 minus 1.5, and this will give me a negative value, minus 0.25. So it means it should be below, and this will make this negative. You know, if the center of gravity is above the pivot, it will make a positive moment, which is clockwise. If the center of gravity of the bar is below the pivot, it will make a counterclockwise moment, which will be negative. So this will be corrected by the sign of L over 2 minus A. Okay, it is very small. It is not zero. We should include it.
الرسمه يعني شوي تخربط لان الرسمه تبين انه بتصير below البيفت بس هي صار
يعتمد على ال values of A, B, and L. Okay, so this can be for any A, B, and L, any values. Okay, so those are the sum of the moments of all the forces, except the applied force. The applied force is plus, because doing if not, sine omega t multiply by a vertical distance. No, L minus A. There is no theta here. Equal to the moment of inertia. The moment of inertia for the bar is about CG is given, which is 1 over 12 ml square. So it is 1 over 12 ml squared plus distance, which is L over 2 minus A squared times M. Theta double that. Plus the moment of the J theta double that of the point mass. We will take this as point mass, which means that JCG is 0 for this. Then we have only M times L minus A squared. Theta double that. Okay, and then you simplify, you add the similar term, the term that have similar multiplied by theta, and the term that is multiplied by theta dot. There is only one term with theta dot, and then theta dot, theta double dot, and this will give you. I will simplify it, but this will take time if I substitute and everything. So this will give us J equivalent theta double dot plus C equivalent theta dot plus K equivalent theta equal to M, what is the force? Equal to F naught times L minus A sine omega t. And F naught times L minus A is torque, is moment. Okay, so this is the differential equation is in terms of theta, and theta is angular displacement, but it is mathematically the same equation of x double dot. So theta, that you can write theta as A, that is the steady state. The question was to find the steady state. And before that, to answer the question for finding C, we will divide by J equivalent. Okay, so that 2 zeta omega n will equal the coefficient of theta dot, which is C equivalent over J equivalent. And from here you will find C, because theta is known. Omega n is square root of K equivalent divided by J equivalent. And for omega n, everything is known because it is not function of C. The only unknown here is C in those two equations. So you can find C because zeta is given equal to 0.2. After that, you find the amplitude, assuming that amplitude is A, will equal to, if you don't want to use zeta, you can use if not times L minus A, minus A, divided by square root of K equivalent minus J equivalent, omega square all squared plus C equivalent times omega square. This will give you the amplitude in radian. This is the steady state amplitude. Okay, so you can do this step by step, substitute for the parameters. We have K1 and K2 are equal. We have A is given, B is given, and to reduce to this. So it's a little bit lengthy, but it will be at the end, second order ordinary differential equation in theta. And we can treat it. This is analogous to the X equation. Okay, question number 4. A spring mass system consists of a mass weighing 100 Newton and a spring with a stiffness of 2000 Newton per meter. The mass is subjected to resonance by a harmonic force f of t equal to 25 cosine omega t Newton. Omega is not given, which means, but the case is resonance. So omega equal to omega n equals square root of k over m. And we can substitute for k is 2000 divided by m, which is 100 divided by 9.81. We can get omega. Find the amplitude of the force motion at the end of 1/4 cycle, 2.5 cycles, and 5 3/4 cycle, assuming 0 initial conditions. The force is cosine omega t, and the question is to find the response or the amplitude at specific time. So 1/4 cycle means tau. So t here for part A is equal to tau over 4. And t for the part B is at t equal to 2.5 tau. And for part C, t is equal to 5.75 tau. And the equation we substitute in is the equation at resonance, X at resonance. For this is undamped system, and this is the total response. We have x0 cosine omega nt plus x0 dot over omega n sine omega nt plus f naught omega n over 2k times t sine omega n t. Okay, so we have 0 initial conditions. It means the first two terms are 0. And then x becomes f naught is omega n, f naught is equal to 25, and omega n is calculated, k is given, and t is given for A, for B, and for C, and you calculate x at those times. That's the meaning of a 1/4 cycle, 2.5 cycles, and the problem is at resonance. Okay, so I will just take you back to the lecture so that refresh what we did. Okay, this is the equation we said is valid for all omega except omega equal to omega. And then we I called equation number 1, which is valid for all omega except omega n. And then number 2 is valid only for at resonance, which is x0 cosine omega n t plus x0 that over omega n sine omega n t plus if not omega n over 2k times t sine omega n t. Okay, and this is the equation to be used, equation number 2. Okay, just make sure here when you calculate sine omega n t, this is in the change the mode of the calculator to radian. Question number 5. Consider the spring mass system with K equal 4,000 Newton per meter, M equal to 10 kilogram, subjected to a harmonic force equal to 400 cosine 20 T. Find this and sketch the total response of the system under the following condition. In order to find the total response, we need to know omega here. As you can see, we have two equations, omega or not equal to omega n and for omega equal to omega n. So the first thing is omega is 20 from the given force. And we need to calculate omega n and compare. If they are equal, then it is resonance. So square root of k over m, which is equal to square root of 4,000 divided by 10 by 10, mass is at 10. It's not 20. Okay. So this is resonance. Then we can use the same equation here. Okay. Initial conditions are given 0.1 meter for the initial displacement, and initial velocity is 0. Okay, so that is just using equation 2 in that slide. 2 more questions. You have a class now, right? So I will. This is about rotating impedance. We will talk about them next time, and then move to the next type of the excitation, which is the support motion. Huh? Only 2, or only 3. The third one is the base excitation. And then, based on that, we will talk about the instrumentation used in vibration measurements. It is based on last part. Okay. We'll see you today at 3 for the quiz, inshallah.